All right, the next thing we're going to look at is work that can be done by rotating objects. And again, by analogy, just like we did before. So when we calculated work with a constant force, that my work was equal to the dot product of the force and the displacement. So we end up having the analog work again, just like before. My rotational work now will end up being the torque, what corresponds to force, dotted with your change in angular position. And again, with your angular position, remember you to find which direction that is, you end up using your right hand rule. So whichever way it rotates, you curl your fingers of your right hand that way, and then your thumb will point in the direction of your angular displacement. Then the dot product depends on the relative sign of your torque and your angular displacement will give you your work. So we'll take an example. We suppose we've got a spool of thread. The spool of thread has a radius of 2.1 centimeters. We end up applying a force of 2.5 newtons on the end of the string. So you can imagine if this was mounted, you can just having a weight there that's providing a force of 2.5 newtons. But anyway, we provide that force at the end of the string. We find the work done if the spool ends up rotating 3.5 times around, 3.5 revolutions. So to do this, we end up finding what my torque is. My lever arm, it was a radius of 2.1 centimeters, so if it's mounted here in the pin in the middle, then my radius is going to be the distance out to where the force is acting, which is 2.1 centimeters. Then my force was 2.5 newtons, and it was on a hanging string, so the angle between my radius backwards and the string hanging down, the angle between those two is going to end up being 90 degrees from what we talked about in a previous thing. So sine of 90 degrees is 1. Multiply all those together, I get a torque of 0.0525 Newton meters. In this situation, the way I've got it drawn, it will be going into the screen. My angular displacement, 3.5 revolutions, so I end up converting those to radians because, again, we're dealing with angular stuff. So then to find my work, it'll be the dot product of my torque and my change in angular position. So the angle between those two, so my torque is going into the page, and so is my angular displacement. It's rotating in that same sense, so curl your fingers around the way it rotates. So the angle between those two, both of them in the same direction, is 0. Cosine of 0 is 1, so you multiply those together, and you end up with a work then of 1.15 joules. And one of the things to note, a radian is dimensionless. In this situation, Newton meters in torque are not joules, but in this situation, it turns into joules because newtons times meters is joules unit. It's just when it's torque, it's not energy. So that's the only little bit of a caveat to watch out for. Okay, so the next thing we're going to look at is for the rest of this period is going to end up being angular momentum. And in order to characterize angular momentum, we end up using an analogy, just like we've done so far, that linear momentum is conserved whenever you have no external net force acting on a system. So by analogy, your angular momentum will be conserved in the absence of a net torque that's acting on a system. So your analogy, P equals mv for linear motion, what corresponds to P is L in angular momentum. What corresponds to mass is moment of inertia. What corresponds to velocity is angular velocity. So L equals I omega. So one thing to be a little cautious on, though, if you've got a single mass, if you have conservation of linear momentum in that situation. A single mass, the mass isn't going to change. So that will end up meaning the mass times velocity beginning is the mass times velocity at the end, which just means your velocities stay the same. That's not necessarily true for a single object with angular momentum, because the geometry of the object ends up being a factor in your moment of inertia. So an example of how that works and how we can conserve angular momentum but not conserve angular velocity for a single particle is the idea of how ice skating works. So if you end up having an ice skater that wants to end up doing a multiple axel, what they'll end up doing, have their legs out, they have their arms point out from their body, and by doing so, the rotation axis is going to be down through the middle of their body. So then by doing that, you end up maximizing the R, the radius. So remember that moment of inertia is when we add up mr squared for all the pieces. So if I take some of the mass and I increase the radius, then I increase the moment of inertia. So by having your arms stretched out, your legs stretched out, you end up maximizing your moment of inertia. So oh gosh, I screwed that up. I wrote L1 omega, it should have been I1. So everywhere you see the L's below the picture, replace those with I's. Whenever you have, at the beginning, the skater will kick off, they'll try to end up getting a significant angular velocity at the beginning. They have their arms stretched out, so whenever they jump in the air, then we end up thinking about what's happening with the forces acting on. The force due to gravity is not small, they don't keep flying up forever, but the force due to gravity is acting at their center of mass, and the center of mass is along the center line of their body. So the lever arm, the distance from where their weight is acting to the axis of rotation, is zero. So even though the force is not zero, the torque is zero because the lever arm is zero. So you have no external torque that's acting on the person, so their angular momentum stays the same. So their moment of inertia times angular velocity at the beginning will equal, when they tuck them in, then your moment of inertia ends up going down. The mass is closer to the center line, and so you've reduced the moment of inertia, so for those to be equal, you increase the angular velocity. So that's the reason why the person will be able to twirl as fast as they do in the air whenever they do a multiple axel, try to end up trying to land that way. So with conservation of angular momentum, you can end up having a change in angular velocity. So that is that bit of analysis. And whenever we have a small particle that is moving, and by smallness, it's the same concept of smallness we talked about before with moment of inertia. We're saying the object is really small compared to the radius of the rotation. So if all the mass is pretty small, then that will end up being the case.